In this video, we're going to talk about HashiCorp Vault. But before we understand what Vault is and what it does, we first need to understand why was it created in the first place. So what problem does it solve? And then talk about how it actually solves the problem. And once we have that foundational understanding, then we're going to look at how Vault works, what are some of the unique features it has, as well as look at Vault's architecture and how it's designed to do its job. So let's get into it. Vault is essentially a secrets management tool. So the question is, what are the secrets and why do we need to manage them? Secrets are generally pieces of information that we use to log in and authorize with different services, like username and password credentials or a token to connect to an API, and so on. And there are two types of users who need those secrets to log into services: human and system users. For example, I as an engineer need to access Kubernetes cluster to administer it or troubleshoot some issues. And CI/CD pipeline, which is a system user, needs access to the cluster in order to deploy and run pods inside. Or another example, me as an engineer would have my user credentials to access AWS account, but Terraform needs its key pair or role credentials to provision infrastructure on AWS. But a very common and large use case of secrets between systems is when our own web application may need access to MySQL database, for example, or maybe another database like Elasticsearch in addition. Plus, our application may be using social media logins from Facebook, Google, so it needs API keys from Facebook and Google APIs. Maybe we're using an external payment service instead of implementing our own, like Stripe. So our application will need to have Stripe API key to make API calls to it. Again, this will be a key to identify our application with Stripe service. So you can guess that anyone other than our application to get hold of any of these keys and use them for evil purposes would be extremely bad for our application because our user data will be leaked, our users won't trust us anymore, and it's going to be a disaster. Now, there are many other secret types, like let's say we have a fleet of servers we're configuring automatically with Ansible, and we provide Ansible with SSH keys to access those servers. Again, if someone else got hold of those SSH keys and accessed the servers, they can basically do whatever they want on those servers and completely mess up our infrastructure. Or think about TLS certificates. We need to create certificates for our applications and get them signed by CA so we can provide a secure connection to our application for our users, where the communication between frontend and backend is encrypted and secure, especially if we are sending user login or payment data, or if we are exchanging any keys between frontend and backend. Or we may have certificates within our systems, like in Istio, for example, to generate certificates for all pods in Kubernetes cluster in order to encrypt the communication between them for better security. So all this sensitive data that we would absolutely not want anyone with evil plans to get hold onto are secrets that we need to protect access to. So as you see, we have sensitive data and access credentials for so many systems and services that other services or human users need to use. Now the question is, where do we keep those secrets? And how do we make sure only the right people or systems have access to them? Well, that's exactly where the challenge begins. In practice, what happens is that those secrets end up everywhere. Engineers may have some secrets locally on their computer, like AWS user access keys to connect to AWS account, or SSH keys or PEM files to connect to servers, or kubeconfig file to connect to Kubernetes cluster. In many projects, you may have some kind of KeyPass files shared around by team members. So when a new junior engineer asks, hey, I need access to the dev database to test my code changes, where do I get those credentials? They may get this password file, or even worse, get a link to a Confluence page which has a list of database credentials for each environment in plain text, which actually happens in real life and is a huge security failure, of course. Or we may even have secrets stored more securely, like in CI/CD pipelines environment variables. So our GitLab CI pipeline or Jenkins pipeline will have a list of all services like Docker registry, AWS credentials, Kubernetes cluster credentials, SSH keys, etc. for all the services it needs to connect to during the pipeline execution. And now you need to, of course, worry about who has access to the section of the CI/CD pipeline settings that allows you to see the values of those environment variables. Now, what about all secrets that our web application needs to connect to databases and API endpoints and so on? We may have some external configuration files with database credentials and API tokens that get passed by, again, CI/CD pipeline, or sometimes they get set directly on the server as operating system environment variables or config files. And finally, another worst case scenario, we may have API keys or credentials hard-coded in plain text in our application source code, which end up in Git repositories and in the commit history of the repositories, which again happens more often than you would think. Or hard-coded access credentials in plain text in Ansible, Puppet, or Terraform scripts. So basically, whether securely stored or completely insecurely managed, those secrets are spread everywhere, all over platforms and servers, engineers' computers, and so on. And this is called secret sprawl. There are two huge problems with secret sprawl. First of all, you have no visibility of who has access to what secrets. Like, what are all the places where we have MySQL database credentials and who has access to those places? It's really hard to know when those credentials are literally just spread around everywhere. If we have secrets in Git repository, either in code or pipeline configuration, again, who has access to the repository itself? Like everyone in the organization, specific teams, specific team members. And on top of that, we actually have no visibility of who has accessed or used what secrets. So if a specific secret was compromised, we wouldn't even know that it happened. And even if we found out, we wouldn't know what leaked the secret. Was it an engineer's laptop? Was it the source code? Was it the application itself or the server? Who knows? So there is no audit trail of who has accessed and used the secrets. And the second problem of secret sprawl is, let's say Stripe API key was stolen. What do we do in this case? We need to delete the old key and create a new one, right? To make sure that the old stolen key is not active anymore or is not usable. In which case, we would need to update all the systems and places where the Stripe key is used. So we need to update the application and say, here's a new Stripe key. From now on, use this one. So the application actually continues to work. And again, when you have no visibility and no proper handling of all the places where different credentials are used, the secret rotation becomes challenging. Or even if we simply rotated the secrets proactively, like change the database credentials once in a while, just to keep all the passwords and tokens fresh and updated, it will still be a challenge to take these new credentials and find all the clients who need those credentials and update them with this new credential. And that's exactly where the secret management tools come in to solve the problem of secret sprawl and all the side effects of it. And Vault is one of those secret management tools, along with some other examples like AWS Secrets Manager or Azure Key Vault and so on. So what do these secret management tools do exactly? They centralize the management of secrets. So instead of having them spread around, we take all the secrets from Confluence pages, server operating systems, configuration files, engineers' local computers, and put it in one central, secure place. However, just dropping the secrets all in there, so we have everything in one place, is not enough. So this is what these tools provide. First of all, instead of plain text, all secrets are encrypted at rest, so while it's stored inside the vault, but also in transit. What does it mean? Well, the secrets need to be accessed by clients, right? So when database credentials are sent from Vault to our application so that our application can use it to connect to the database, the credentials need to be encrypted when they're sent from Vault to the client in transit. This means even if someone caught the credentials while in transit, they still won't be able to read them. So that's another security layer. And as engineers learn continuously in our DevSecOps bootcamp, security is layered. So it's not one giant wall that you build around your system. It's layers of walls, like peels of onions. So that if someone hacks into one layer, they basically have to overcome the next one and the next one. The more layers you have, the harder it is for malicious actors to steal your data or secrets and at any point in time get access to something that allows them to access your entire system. And because security is layered, the story and use cases of secrets management tools continues. Now we have secrets in one place, encrypted, at rest, and in transit. Now we want to control who can access which secrets, right? So which humans and system users can access what secret stored in the central place. And for that, those tools have access control. Like not every service needs access to database or Stripe API key, right? So we configure granular access management to make sure that engineers as well as applications only have access to those secrets that they explicitly need. So now instead of everyone in an organization that has access to CI/CD pipeline seeing the secrets configured there, now you need explicit access to the secret to see it in Vault. And on top of that, we have auditing. So we can see what secret data was retrieved or accessed by web server at what time, what credentials were accessed by different engineers. So auditing is like having cameras in a building. So if someone breaks in and steals something, you can see what happened exactly. You have a trace that was left that tells you exactly what happened, in which order, at what time. So basically, we're moving from having everything spread around with no visibility to having them in one central place with tighter control over them and visibility on how and when those secrets are used. Now we're storing secrets centrally with tight access control, so humans or applications can access the secrets securely. But what happens once the application actually gets the secret out of Vault? What if the application can't keep that secret safely? What if some junior developers edit some log lines for debugging that just logs out the entire information with the sensitive data to the console? Happens more often than expected in real life. If we have a log collector and processor, those logs will be sent to a central storage and then off to a log visualization tool. So now those secrets are exposed to anyone who can access the log storage or log visualization tool. So how can we secure the secrets even after they get fetched by the application? That's where the dynamic secrets feature comes in. The idea is really simple. Basically, instead of using static credentials like username and password or API keys that don't expire, Vault lets you create short-lived credentials with short expiration period, like valid for 10 days or maybe even one-time use. These are created dynamically when the application or any client requests the secret and expires after the validity period. This means now even if the application leaks the credentials into logs, it's not a big issue because by the time they end up in logs dashboard or someone finds them and tries to use them for bad purposes, they may be expired already. So with short-lived access tokens, security risk is minimized. Even if someone gets access to the token and it is still valid, they will have a very short window to hack into systems with that credential. And in hacking, usually hackers need to probe around for a long period of time to get into systems. So limiting the time in which they can do damage already reduces a risk tremendously. Now, from an auditing point, this is also very interesting because with dynamic secrets, every client will get its own unique short-lived credential. So if we have 5 clients who access database credentials, they will all get their short-lived unique credentials. So if that database credential gets leaked, we will know exactly which client was the vulnerable source. And this is important because now you know there is a specific microservice or application or client that needs to be secured because it is exposing sensitive data. And of course, that credential needs to be rotated only for that application. We don't need to rotate the access credentials for any other client, which is a huge advantage for operations because revoking credentials to a system, like rotating credentials of a database would usually cause a short outage for the clients who are accessing this database. So we're preventing this outage for all other clients who didn't have any issues. So the ability to isolate that incident and pinpoint the exact client that was compromised is a huge benefit in secrets management. Now, apart from the actual secrets, we also have regular data which are not considered secrets but still need to be protected. These are personal data of our users, also called PII or personal identifiable information, which basically means information that you can use to uniquely identify someone. And lots of applications store your personal information, right? Your birthday, email address, phone number, maybe social security number, and so on. Now, these aren't considered secrets, so you wouldn't store them in Vault or a secrets management tool. Instead, they will be stored in a regular database along with other application data. But there are security implications of the PII being exposed. Now, you may be thinking, why is that a big deal if this kind of information gets exposed? Because a lot of them may be public already. Well, hackers can actually use this information to craft very convincing personalized emails or messages for phishing attacks, for example. In many cases, there are even government regulations and penalties if a company does not properly protect their users or customers' PII. So that means if you're storing personal identifiable information, this data also needs to be secured. Now, of course, we have database credentials to secure access to them, which already is one layer of security. But you will hear me say this again, security in layers. And that's where Vault's feature of Encrypt as Service comes in. Again, very straightforward and simple idea. We can encrypt data in a database using Vault, where Vault will handle the entire lifecycle of the encryption keys and encrypt the data securely. So now we have database credentials stored in Vault, encrypted, or maybe issued as dynamic short-lived credentials. But in case hackers still manage to break into the database, again, as I said, a client was compromised and the credential was stolen, they still won't be able to see the data because it's encrypted instead of plain text. So they would actually need to get the encryption key from Vault in addition to be able to decrypt and read the data stored in the database. So even with the database credentials, they won't be able to access that personal user information. Now, this is actually one small lecture in a pretty large secrets management chapter of our DevSecOps Bootcamp, which is a massive program which covers everything from security in software development to DevSecOps pipelines, cloud security, Kubernetes security, compliance as code, GitOps, and tons of more important concepts. That's why it's no wonder why DevSecOps or DevOps engineers with security skills are so highly demanded and hugely well paid, because it's a vast knowledge of very important skills that all the large companies desperately need. If you want to know what DevSecOps is all about and what skill set it covers, you can grab the detailed DevSecOps curriculum from below that you can use to learn about this important concept in engineering. Hope you find it useful. Now back to how Vault works. You understand what secrets management tools are, why they exist, and some of the additional use cases that Vault specifically provides. Now the question is, how does Vault actually do all of this? How does it work? How does it store the secrets? How does it manage access to those secrets and provide the feature of dynamic secrets as well as encrypt as a service? Well, at the core of Vault, we have what's called the core, which has all the components for managing most of the work that Vault is doing. And to talk to that core, there is a layer of Vault API, and Vault is API driven. So whether you are talking to it via UI or CLI, all requests go through the API. Now for storing different types of secrets, Vault has different what's called secret engines or secret backends, which is part of that Vault core. The simplest one is key value store, which is a generic secret store where we can store arbitrary static secrets like username and password, API keys, database credentials, and so on. But remember, I mentioned the dynamic secrets feature. Well, for those, there are other types of secret backends. For example, Vault has various database secret backends, which will dynamically manage secrets for different databases like MySQL, Oracle, Postgres, and so on. On the official documentation, you can actually see a full list of database secret backends. There is also RabbitMQ for dynamic credentials for message queues. We also have AWS. So if we have applications that need to access S3 bucket, for example, but we don't want to give static IAM credentials to our applications, instead we can define a role and then dynamically generate short-lived credentials as needed. Another common use case is PKI, or public key infrastructure, for certificate management, which is a very complex process for operations engineers. So we often have very long-lived certificates, like 5-10 years, because engineers do not want to go through the process of generating and rotating them. With Vault, we can programmatically generate the certificates. So in practice, people can use short-lived certificates, maybe a couple of days or maybe even hours. We also have SSH secret backend for generating the SSH keys dynamically. So you don't have a single SSH PEM file for your entire fleet of servers. Instead, you can create one SSH key for each one of them. So in case a PEM file gets compromised, it doesn't affect all your servers, but rather that incident can be isolated for that one specific server that the PEM file belongs to. There's also secret backend for Kubernetes for generating Kubernetes service account tokens. So Vault basically ties in the mechanisms of these different tools like AWS, IAM service, database, access management, Kubernetes, RBAC. So it uses the existing mechanisms of those tools to create temporary credentials for the clients. So it basically acts like a broker of authentication between the client and all these different services. So Vault interacts with these tools to create those temporary credentials and would return them to client. And that's why you have a specific secret engine for each tool. And the way it works is once you install and set up Vault, you have the core of Vault installed, and then you can enable different secret backends that you need. Now, these secrets need to be stored somewhere, right? Like physically stored in a location. And these are storage backends. This can be a standard relational database like MySQL or Postgres. It could be HashiCorp console. It could be a cloud-managed database service. And as I mentioned, in Vault, we only store secrets, the actual sensitive data, which are credentials. So the volume of the data is not as large as the standard application data. So we don't need large database, but we do need high availability and replication of data to make sure the data isn't lost. Because if the credentials are only stored in Vault, and if we lose those credentials, then we're going to be locked out of our systems. Okay, so we have different types of secrets stored in some storage backend, database. Now, these secrets need to be securely accessible, right? So basically, we need secure login mechanism into Vault. We need a way to authenticate with Vault to provide an identity, like, hey, I'm Nana from DevOps team, or hey, I am EC2 instance from AWS account with this ID, or hey, I'm pod from Kubernetes cluster with this name. And we also need authorization, like, can I please get credential for the Postgres database? Or can I please access the S3 bucket called this name? Or can I get the Stripe API key? And for this, Vault uses so-called authentication methods or authentication backends. Vault uses this to authenticate clients from different systems to fetch the secrets. For example, we may use AWS authentication plugin. So if AWS resource like EC2 needs access to a secret from Vault, it can authenticate via AWS plugin. We also have Kubernetes auth plugin. If Kubernetes component like pod needs to access secret in Vault, it can use Kubernetes auth plugin. For human user, we may use something like LDAP or Active Directory auth plugin to prove our identity. The idea here is that instead of Vault identifying each specific entity, like Kubernetes pod, an AWS EC2 server, or a human user by itself, it uses a system that it trusts, like Kubernetes, AWS, LDAP, and so on, to identify these different entities. And this is generally how identity provider concept works. So Vault trusts Kubernetes, AWS, and then Kubernetes and AWS provide their components with a stamp of identity that these components can present to Vault to identify themselves. Like Kubernetes gives its pods or services identity saying, this pod is from my cluster, or AWS gives its services identity. So Kubernetes and AWS are essentially identity providers for Vault. And that's why we have the term. So in order to log in to Vault, a client, which can be human user or an application, can send a request using a specific auth method at a certain path, because everything in Vault is path-based. And Vault will use that auth method to authenticate the client. If this is successful, then the client will get a token as a response. And that token has Vault policy associated with it, which basically defines what permissions that client will have using the token. So what secrets they can access, at which path, and so on. And following the best practices, of course, this token is short-lived. It's a dynamically generated credential, so it expires after a certain validity. And that means the client has to re-log in or re-authenticate to renew the token. So now when a client wants to fetch some data from a secret engine in Vault, it will send a request along with the token that it received when it authenticated with Vault. So for example, with a key value store, which is the simplest secret engine, client makes an API call to Vault at a certain path. Vault will check the token and the policy that defines whether this client actually has permission to access the secret at this path. And if successful, Vault will basically send back the actual key value pair of the secret. And same way as secret backends, you can enable any of these auth backends that you need after you have installed and set up Vault. And finally, we need the audit trail, right? We want to track who has accessed what, when, how many times, and so on. This is the visibility of who is using the sensitive data in case of any secrets being exposed or compromised. And you probably already guessed, we have audit backends for those, called audit devices. So audit devices are the components in Vault that keep a detailed log of all requests to Vault and their responses. Because every operation with Vault is an API request response. When using audit device, the audit log contains every interaction with the Vault API, including the errors. So Vault connects to an auditing backend, which again is an external system that you can plug in and streams out request response auditing to it to create a trail of who's done what, or who is doing what in Vault, who is fetching the secrets, who is updating the secrets, generating dynamic secrets, and so on. And this audit log can be a simple file or syslog, and you can actually send audit info to multiple audit backends. So as you see, Vault has this pluggable architecture design where you have the core, and then you can connect or plug in different auth methods or audit devices, secret engines, or storage backends to it. And this type of architecture makes it easier to integrate Vault with different platforms and services. So this makes Vault flexible in that sense. So with Vault in place, the way it works now is Vault manages clients that are authenticating against different set of identity providers. We then log the access in different trusted sources of log management tools. We store the secret data in any durable system, and we can store either static or dynamic secrets using different secret backends. So I hope now you understand clearly what Vault is and the secrets management concept in general. My main mission is to break down these seemingly complex technologies into such simple explanations that you are just much more excited and motivated to learn them for your engineering career. And that's how I designed all our educational programs, which you can browse on our website if you're interested. With that, as always, thanks for watching and see you in the next video.